The group members are Justin Rehagen and Justin Echinatu. I'm going to briefly go over some of the stuff that we've already covered before. Some of the background, the steady-state operating curve, step response, FOPDT model, and sign response, buddy graph and model, and then go over a little bit of the new stuff, the root locus model today. This is our system. The computer interfaces with the JRC to the variable frequency drive to control the motor to run anywhere from 0 to 100%. Turns the generator and lights up the lights and interfaces with the computer through the ERT system there. This is a picture of our three-phase motor, 5 horsepower, turning the generator with the coupler there in between the two of them. Block diagram showing that the only thing that we have control over is changing the input. The system is as the system is, and to change the output, we just adjust the input. This is an example of one of our steady-state operating curves. The input is at 87%, and at that input we have an output of 74 volts. We did quite a few of these to plot on a steady-state operating curve to give us our slope, or so we were able to measure the slope and calculate our gain, or K. In this case, it was 1.8 volts per percent. Next, we did the step response. In this example is step from 85 to 90%. It was at 85%, the steady state was around 70.5% or 70.5 volt output. And after the 5% step up, steady state reach was 79.2 volts. Again, we plotted several of these step up and step down to be able to calculate the different parameters for our system. Primary one that we were concerned with here is gain, 1.4 volts per percent for the step up and 1.6 volts per percent for the step down. For the steady state operating curve, we had 1.8 volts per percent, so it's fairly close. Our dead time for the step up and the step down was very similar, 0.035, 0.039, and the time constants as well were also very close to each other for the step up and the step down. The next models the step response, and the primary thing here on the step up and the step down is that the model follows very closely to what the actual experimental data was. There's very little differentiation there. In the three ranges that we had for our customer, we had an 80 to 85% step up, and 85 to 90, 90 to 95%. And it shows here on the slide the gain for this. The 1.5%, for example, for the 80 to 85, 1.5% is the actual or the experimental data, and 1.7 was the model data. Similarly, we did the same thing for the step down. There's 1.5% versus 1.3% of the step down for the actual versus the model, for example. The model versus the actual or experimental time constant, tau, dead time for the step up and the step down response here. The numbers are very similar between the model and the experimental data, as I mentioned earlier. The next thing that we did was a sign response, so that we were able to put together the Bode plots. This is an example of 0.1 hertz sign response for 75% input. We calculated the difference here, the delta M over delta C, which gave us our gain, and then calculated the phase shift, the difference in shift and phase angle, to be able to calculate some of the other parameters here. Plotted it all on the Bode plot here. This is our actual numbers that we got. An example from the 80 to 85% range. It shows that our ultimate amplitude ratio is 0.24. Our K here was 1.5, which was still in range with our K that we found by other methods. Ultimate frequency is 5 hertz, and our KCU is 4.2% per volt. Very similar results for our model Bode plot. And then to compare the two, on the gain for the 75% range was the only one that we had any significant or any difference. It was 1.3% for our experimental data, 1.4% for the model data. The other two were identical. Our T-naughts were very similar, and the taus, our range that we were operating in is very linear, and so the numbers that the three of us had for our 3 different sections of our range all turned out to be very similar to each other. The FU is 9, 7.5, and 7 for the 3 different ranges. Ultimate amplitude ratio, again, very similar for the 3 different ranges. Comparing the two, the calculated system parameters versus the model system parameters, again, they're very similar. The average FU, for example, is 6.5 and 7 for the model system is the biggest difference that we found. Everything else was almost identical. The damping effect, this is the graph showing the decay ratio. The ratio between the first and second peaks gives us the decay ratio, and we can adjust this by adjusting the K to conform to the output that our customer wants. If they want higher or lower overshot there. We use the data that we collected here to plot our root locus plot using Excel spreadsheet. The angles that we found here are related to the different damping effects. Again, the ratio of the first and second peaks. A 45-degree angle is the 1 to 500th decay, and quarter decay is 78%. Found our critical damping to be fairly close for the most part for the 3 ranges that we had, 0.59, 0.5, and 0.16. It seemed to getting smaller the higher that we got, the higher that our input was. Almost identical for our 1 to 500th decay, KC1 500, at almost exactly 1.2 for each of them. Our 1 to 10th decay was, again, very similar, 2.6. And quarter decay at 3.5 is the average. And our ultimate KC, where the marginal stability was, is approximately 5.3 to 6. It's the highest range. That's it. Any questions?